Welcome to lesson 2.1 on relations and functions. My name is Mr. Teal, and I'll be taking you through lesson 2.1 today. Unfortunately, I'm having a very bad hair day, so I will not be sharing my camera with you, but you get to look at my little, graduation picture talking as you learn the lesson today. So have fun with that. And let's go ahead and get started. So we'll go over some vocabulary first to introduce the concept of relations. We're going to really expand upon relations throughout Unit 2. So we're going to go over some introductory vocabulary today. So first of all, in this chapter, we begin to explore relations, which are a set of pairs of input and output values. So if you think about ordered pairs on a graph, coordinates on a graph, there's an input and an output, an x value and a y value, and a set of these x values and y values represents a relation. Relations can be represented as ordered pairs, mappings, tables, and graphs. Now, the set of all inputs or x coordinates of the ordered pairs are called the domain of the relation. So all of the possible x values, all of the possible inputs of a relation put together represents the domain. On the other hand, the range represents all of the set of outputs or the y coordinates of the ordered pairs. When a relation in each element of the domain corresponds with exactly one element of the range, then we call the relation a function. So if all of the inputs have exactly one output, all of the x values have exactly one corresponding y value, that means that our relation is a function. And we'll talk about that a little bit later on. Now, when we're given a graph, we can use the vertical line test. And this test helps us determine whether a relation is a function. So if a vertical line passes through more than one point on the graph of a relation, if we use the vertical line test, that's a test that we use to determine whether a relation is a function. If the vertical line passes through more than one point on the graph of the relation, then the relation is not a function. So if we were to draw a vertical line through any given point on a graph, we only want that vertical line to touch the graph once. If it touches the graph once, the relation is a function. If it touches more than once, then that relation is not going to be a function. If it touches more than once. So going down to where it says if f is the name of a function, the function notation f parentheses x, this is read f of x, shows the function's name is f. So if we have f of x, that means the function's name is f. If we have g of x, that means the function's name is g, and so on. And this also represents the range value f of x for the domain value x. So the f of x represents the range, that's the output if you have an input x. So just know that f of x is your output. So if you're thinking about it, we might see f of x equals something or y equals something. Those are really interchangeable because both of those represent the output or the range of a relation. Moving on, you read the function notation as f of x. So just like we said before, that is going to be read f of x, or a function of x. Now note that f of x does not mean f times x, so even though we have f parentheses x, that might look like multiplication. However, f does not represent a variable, only x does. So f is just going to be the name of the function. Now, when given a function, the independent variable is x. On the other hand, the dependent variable f of x represents the output of the function. So depending on what we plug in, so whatever we plug in for x, that is going to determine what our output is. So that means the variable f of x is the dependent variable. The output value depends on the input value. Again, that is why we call it dependent. Now moving down to example number 1. So we are going to represent relations. Before we do this, I do want to talk a little bit more about what a function is and how to determine if a relation is a function. So I'm going to go ahead and write down a series of points, x and y. Now for my x values, instead of doing numbers, I'm just going to go ahead and write names. So let's say we had Mr. Teal. Then we have, let's say, Miss Christensen. And we also have Miss Muko. These are all the teachers, math teachers that we have in the 700 hall. So let's, so X values, we're gonna have names. Let's say for Y values, we have restaurants. So let's say Starbucks. And then I'm also gonna say Chipotle. and McDonald's. So I want you to pay attention to what I'm about to say. Now, we're going to talk about when a relation is a function. So let's say Mr. Teal is at Starbucks, Miss Christensen is at Chipotle, and Miss Muko is also at Chipotle. That is a function. Mr. Teal can be at Starbucks while Miss Christensen and Miss Muko are both at Chipotle. In other words, I am allowed to have one output, and Miss Christensen and Miss Muko also have one output, which is Chipotle. Now they have the same output, but that's okay because two different people can be at the same place at once. Two different X values or two different inputs can have the same output. Now, on the other hand, I want you to think about what if Mr. Teal was at Starbucks, Chipotle, and McDonald's all at the same time? Can Mr. Teal be in three places at once? No, because I can only be at one of these three places. So in other words, one input cannot have multiple outputs. Mr. Teal cannot be at all three of these places at once. So every single X value needs to correspond to only one Y value. We cannot have multiple Y values for any given X. So let's go ahead and look and see if this relation is a function. So there's a couple ways we could do this. The first way, we could create a table of values. So let's go ahead and look at some of our coordinates that we have on this graph. So we're going to write some of the ordered pairs. So I'm going to start at -2. So at -2, my coordinate point is going to be -2, comma, -1, 2, 3, 4. So I have -2, comma, -4. Then let's do -1. At -1, I have -1, comma, 1, 2, 3, -1, comma, -3. At 0, I have my y-intercept at 0, -2. Then at 1, I have 1, comma, -1. And at 2, this is my x-intercept, I have 2, comma, 0. So the first way to determine whether or not this is a function, we can look at all of these values and see if every x has exactly one y and we don't have multiple. So if you see, we don't have any sort of funky things going on. We don't have Mr. Teal being at three places at once. So this can help us determine that the relation is in fact a function. The more accurate way to do this, I would say, because we don't have the whole list of outputs, what we could do instead is we could use the vertical line test. So if we hold a vertical line to this graph and slide it across the graph, at any point, do you see this graph touching more than one point on the line? No, the line is only touching one point on the graph at any given position. So that means this passes the vertical line test. I'm going to call that the VLT, passes the vertical line test. That means this relation is, in fact, a function. Every input has only one output. All right, let's go ahead and move on to the next page. So example number 2, in the mapping below, write the relation as a set of ordered pairs. So the cool thing about relations is that we can represent them in a number of different ways. We see graphs, we see tables, we see this diagram. So there are many different ways to represent it, but the common theme is you can represent a relation as a set of ordered pairs. So if we look at each one of these x values, there's an arrow pointing to its corresponding y value or its output. So the first ordered pair that I can write, and it's really simple, -5 is pointing to -2, so that means the input is -5, the output is -2. My first ordered pair is -5, comma, -2. Next, I have 0 pointing to 1, so that means my next ordered pair is 0, comma, 1. My third one is 2 is pointing to 1, so I have 2, comma, 1. And last but not least, I have 4 pointing to -3, which means 4, comma, -3 is my next ordered pair. Now, this is how we represent sets of ordered pairs. We just put these funky looking brackets and we put all of the ordered pairs next to each other with commas in between. I almost forgot what that word is because I am not an English teacher. I am a math teacher. I do not know what commas are. So now the next question is this relation a function? Well, like we said before, every input can only have exactly one output. So if you look and see, all of these inputs only have one output. They're only pointing to one number. Yes, 0 and 2 both point to 1, but like we said, Mr. Teal can be at Starbucks and Miss Christensen can also be at Starbucks. So two different inputs can have the same output. That is acceptable. So I'm going to say yes, this is a function. Okay, let's move down to domain and range. So now that we introduced this concept of ordered pairs and inputs and outputs, we're going to relate that to the domain and ranges of functions. So let's find the domain and range in each of the relations below. Now, like we said before, the domain represents all of the possible inputs or x values of a relation. The range of a relation describes all of the outputs or the y values of that function or the relation. So let's go ahead and look at the domain. So the domain is all of the possible values for inputs. Since we have this set of ordered pairs, what we are going to do is we are literally just going to take all of the individual x values or the inputs, and that's going to represent our domain. So our domain is all of the following values. We have, let's see, what's our smallest x value? I want to put this least to greatest just to keep it nice and organized. So let's go ahead and look at our smallest x value. Well, since I'm looking at just x values, -2 is going to be my smallest x value. So I put -2. My next smallest x value is going to be 1. So I put 1. Then I put 2. And then I have 2 8s. Now, what I'm going to do, since 8 is represented 2 different times, I'm just going to put it once. Okay, because it's already included in the domain if I just list it once. Now, looking at the range, like I said, the range is all of the possible outputs of the relation. So if we look at all of the outputs of the relation, that is going to represent our domain. Excuse me, our range, my bad. So let's go ahead and look at this. We have -3, 4, 8, 6, and 7. -3 is going to be the smallest, so I'm going to put that first. We're going least to greatest. Then I have 4 is the next smallest. Then I have 6, 7, and 8. So this is all of the possible outputs or y values of that relation. So that is going to be my range, all of the individual y values. Now ask yourself, is this relation a function? Remember, in order for a relation to be a function, all of the inputs must have exactly one output, not multiple outputs. And if you take a look at this one, I'm going to go ahead and highlight it. 8, -3. If you look at this ordered pair, and you also look at this ordered pair, 8, 6, you will see that both of these have an x value of 8. So that means 8 has 2 outputs. 8 has an output of -3, and 8 also has an output of 6. Since this x value has 2 different y values, 2 different outputs, that means that this relation is not a function. Mr. Teal cannot be at Starbucks and Chipotle at the same time. He can only be in one place at one time, so this is not a function. All right, let's move down to part B. So if we're talking about the domain and range of a graph, it's very similar. So we're going to first look at a graph of a parabola. So what I want you to do first, let's go ahead and determine very quickly if this graph is a function for part B. So in order to determine if the relation is a function and we are given a graph, we're going to use the vertical line test. So since this vertical line does not touch any more than one point at any given time, this means that this relation is a function. It passes the vertical line test. Let's say passes VLT. Okay, and then also something else I want you to note about this function, it is continuous. There is a straight line being drawn, and that's going to help us determine what our domain and range is going to be. Okay, so if you want to look at your domain, keep in mind your domain is all of your possible x values or all of your possible inputs. Now, since this is a continuous graph that goes forever and ever to the left and then forever and ever to the right, our domain is all real numbers on that x-axis, okay? Any one of these numbers on the x-axis are going to be represented by this graph because it goes down into the left forever and down into the right forever. So our domain is going to be all real numbers. Now, how we write that is we are going to write -infinity to +infinity. That's how we represent all real numbers on that x-axis. Now we're talking about the range. The range is all of the possible outputs or y values of that relation. Okay, so if you look at this graph, you might notice that there is a peak to the graph. This is the highest point that the graph goes. Above this point, there are no more points on that graph. So the range or the output is going to stop at 2. It doesn't go any higher. So what I'm going to say is, since all of these values are possibilities for outputs, I'm going to say negative infinity, because my graph can go all the way down. However, I am stopping up here at 2 when my y value gets 2. So I'm going to say I'm stopping at 2. Now, since 2 is hit on the graph, it's included in the graph, right? The graph goes through that point when the y value is 2. I am going to do a bracket instead of a parenthesis. Now, a couple of rules about brackets and parentheses. Let's go ahead and write these down. This is what we call interval notation. So if we have 2 parentheses, all right, with our domain or our range, what this is saying is that the value that is next to the parenthesis is not included. So if you think back to when we were talking about inequalities, the inequalities, if we didn't have the equal sign underneath the inequality, that meant that the value was not included. Kind of the same concept here. If we have a parenthesis, that means that that value is not included in our domain or our range. Now, if we have brackets, on the other hand, this tells us that both of the values next to the brackets are included. Okay, now we can also have a mix of these two in the same. So as you see for the range up here, we had a parenthesis and then a bracket. That's a possibility. That means that this value is not included in the domain or range, but this value is. And we could also have a bracket and then a parenthesis. That's also acceptable. Okay, now just a quick note. When we are referring to infinities in either our domain or our range, we are always going to put the infinities in parentheses and not brackets. Okay, and this is because we don't have an exact idea of what infinity is. We don't exactly know what concrete number that is. And since we don't have a concrete idea of what that number is, we're just going to put parentheses around it, but it still represents all real numbers. Okay, let's go up to part C. So for part C, we're going to first determine if this relation is a function. So I'm going to do the vertical line test because I have a graph. And if you notice, immediately when I hold that vertical line to the x value of 1, I pass through 2 different points on that graph. So this means we do not pass the vertical line test. So we do not pass the vertical line test. That means this relation is not a function. Oops, I didn't leave myself enough room, not a function. Okay, so another thing to note about this graph, as we can see, there is no line going on here. We just have a bunch of coordinate points, a bunch of ordered pairs right here. So I'm going to say, since this does not have a line through any of these, and it's not going off in any direction forever, instead of being continuous, this graph is a discrete graph. Okay, so we have the continuous graph on part B, and we have the discrete graph on part C. Now the domain is going to be a little bit different because we only have specific points where this graph is representing ordered pairs. We don't have any points in between those coordinates. So for that reason, our domain and range are going to be a little bit different. So let's go ahead and talk about this. So since I have a series of coordinates right here, I'm going to make my life easier just by writing down what each of those coordinates are. So if I look at this point right here, that's going to be 1, 1. And then I also have 1, -3. Then if I look at these points right here, I have -2, 0. It's a -2. And then I also have a -2, -2. And finally, my vertex right here is going to be -3, -1. And these are all of my ordered pairs. So the domain is going to be all of the possible x values of that function or inputs. So I'm going to go ahead and do what I did above here in example number 3. And I'm going to include the set of all of those numbers. So all of my x values, let's go ahead and look for my smallest one. My smallest x value is -3, so that's going to go first. Then my next smallest is -2. I'm only including those once, even though they're repeated. And my last one is 1. So these are all of the possibilities that I have for x values. Now let's look at all the possibilities that I have for y values. So my smallest y value is going to be -3. So I'm going to include -3. My next smallest y value is going to be -2. After -2, I have -1 as well. I also have a 0 for y value. And I also have a 1 for a y value. So all of these numbers are possibilities for those outputs. So since we just have points and we don't have any lines up here, our domain and range are only represented by specific numbers, specific inputs and specific outputs. All right, moving on to page number 3, let's look at example 4. So is the relation a function? Explain why or why not. So if we look at part A, we're going to go ahead and see, do any of these y values have the same x values? So do any of these inputs have more than one output? So let's look at -2. -2 corresponds to 6, 0 corresponds to 3, 1 corresponds to -1, 3 corresponds to -4, 1 corresponds to 7. If you'll notice, these two numbers are the same. We have two of the same input. However, these inputs, so if we input 1, we can get -1, and we can also get 7. So what this means is we have 1 corresponding to 2 separate outputs, -1 and 7. This is saying that Mr. Teal is at both Starbucks and Chipotle at the same time. That input has 2 outputs. That is not acceptable for a function, so we're going to say this is not a function. Now, before we explain, let's go ahead and look at part B. So part B, we have these 3 x values and these 4 outputs. If you'll notice, 4 is pointing to 2 separate numbers. We have 4 pointing to both -1, and we have it pointing to 3. That means the input of 4 has 2 separate outputs. Mr. Teal is at Starbucks and Chipotle at the same time. That is not possible, so we are going to say that's not a function. If we want this relation to be a function, all right, then it can only have 1 output for each input. So I'm going to go ahead and say that A and B are both not functions because on A, 1, -1 and 1, 7, we have the same input and different outputs. So I'm going to say same input, different outputs. And then on B, we have 4, -1, 4, 3. Again, same input, different outputs. And also, just to note, if we were to draw these graphs of the relations, they would fail the vertical line test. Okay? So just keep that in mind. They are not functions because they have more than 1 outputs for 1 single input, and they would fail the vertical line test if we were to draw them on a graph. Moving down to example 5. Vertical line test. Determine whether the relations shown below are functions using the vertical line test. Can you name the domain and range for each relation? So on part A, if we include the vertical line test, I'm going to use my pen here. Does my pen cross through any more than 1 point as I go left and right on the graph? No, I'm only touching 1 point at a time. So that means that this is a function. So I'm going to say yes, because it passes the vertical line test. The domain of a parabola, keep in mind, this is going up forever to the left and forever to the right. So that means the domain is going to be all real numbers. And like I said before, I represent all real numbers by saying -infinity to +infinity. Okay. Again, I'm including parentheses around those because I don't have a concrete idea of what infinity is. So I'm just going to put parentheses instead of brackets. And then my range, remember, I don't have all of these values for infinity represented by the graph. My graph starts right here at the y value of 2. So that means starting at 2, going up forever and ever and ever to infinity, I have y values. So my range is going to be 2, and 2 is included because that's part of the graph. And it goes up to +infinity with a parenthesis, because again, infinity is not concrete. Looking at part B, so I want to see, does my vertical line test pass or fail? If you go right here, and I draw a straight line down here, as you can see, that straight line touches at all of these points right here. So the vertical line is passing through multiple points on this graph, and this does not pass the vertical line test. So I'm going to say no, fails vertical line test. Now, the domain of this function, this does not have arrows, okay? We have two segments at the end. That means that this graph stops at this point and this point. So my domain is not going to be all real numbers because I stop at these points. So let's go ahead and figure out what these x values are. So if I go to the left of my y-axis, this is -1, -2, -3, -4. So that's an x value of -4. So this means my graph starts when x is -4. So I'm going to say my domain is from -4. Again, that's a solid dot, so that means that -4 is going to be included because we are representing that on our graph. And our domain ends at this point right here, which is 1, 2, 3, +4. Okay, so from -4 to +4, those are all of the possible x values. Even the decimals in between, right? Now for the range, we're going to see what this point is. Now, what is the lowest point on the graph compared to the highest point on the graph? So let's go ahead and take a look at this. Our lowest point on the graph is right here, okay? So that means that's where our y values start. The highest point on the graph is going to be right here. So that means all of the y values have to be in between those two y values. So my first y value is going to be starting at -2, because we have to go down -2. Okay, and they are going up to +1, 2, 3. Okay, so all of the possible y values are starting at -2, going up to +3. They are included once again, so we're going to say starting at -2, going up to +3. All right, let's go ahead and move on to the next page. So example number 6, I have f of x is equal to 3x minus 5. So find the output for the given inputs in the table below. I'm actually going to use my calculator here just to plug them in. You can do these by hand easily, but if you have a calculator, just plug it in. So what we're going to do is we're going to find the output for the inputs. That means we're going to plug in these values for x. So if I'm looking at -3 for x, all I'm going to do is plug in. So I'm going to say plug in. Okay. So now if I plug that into my calculator, I'm going to have 3, because f of x is 3x minus 5. I have 3. I'm plugging in -3, so 3 times -3 minus 5. That is equal to -14. Okay. Then if I'm plugging in -1, 3 times -1 plus, minus 5, that is going to give me -8. And I'm going to do the rest of these. 3 times 0 is 0 minus 5 is -5. I don't need my calculator for that one. 3 times 1 minus 5. -2, 3 times 2 minus 5, it's going to be +1, and then 3 times 4, minus 5 is equal to +7. Okay, nice and easy. Moving down to example 7, we're going to match each equation with the situation. This is under writing functions. So for number 1, Tom buys a book with a $50 bill. The change he gets from the cashier is a function of the price of the book. Okay, so $50 bill that he's using, and the change he gets from the cashier is a function of the price of the book. Now, since we are talking about price, I might want to call that P. Okay, and listen, so the $50 bill, that is going to be your constant, right? That is what you start with no matter what. So no matter what the change that you get is, or whatever that is, like we have $50 is your constant. So we want to look for a function where $50 is the constant. Now, if we're looking at C, C is the only function here that has a constant of 50. So that means that C is going to represent number 1. Number 2, Rick rents a scooter for $50 a day. His total cost is a function of the number of days he rents the scooter. So there is no other things that we need to know other than he rents a scooter for $50 a day. The total cost is a function of the number of days. So depending on how many days he rents the scooter for, that's going to determine how much he pays in total. So that can easily be represented by multiplying $50 times however many days he is out with the scooter. So the function that would represent that is going to be B. Because if we look at B, we have 50 multiplied by the days. That is what represents this situation. Part 3, some friends want to share equally the cost of $50 lunch receipt. The price each friend pays is a function of the number of friends. So If you are at lunch with your friends and the total bill is $50 and you want to split it 3 ways, you are obviously going to divide the total cost of lunch by 3 because that's what you want to do if you have 3 friends that are sharing lunch and you want to figure out how much they each have to pay. That is represented by A because we're dividing the total cost of the meal by the number of people that are attending the meal. That's going to be everybody's individual cost. So just being careful to look at the situation, figuring out, okay, do I have a constant? Okay, how am I doing this? Am I dividing? Am I multiplying? That is going to be the giveaway when you're trying to figure out what equation represents that situation. Moving on to example number 8. Writing functions to model real-world applications. You are buying bottles of a sports drink for a softball team. Each bottle costs $1.19. What function rule models the total cost of a purchase? Evaluate the function for 15 bottles. So I'm first going to go ahead and relate some things. So the cost, again, we're buying bottles of a sports drink for the softball team. Each of them costs $1.19. What function rule models the total cost? So the cost is going to be the price of the bottle times the number purchased. Okay, so if you're buying a bunch of these drinks for your softball team, in order to find the total cost of that, you're going to have to look at the number of bottles you're purchasing and the price of the bottle. That's how you're going to find your total cost, right? Now we're going to say we need to define our variables, right? So we're going to say that C is equal to the cost and B is equal to the number of bottles that you are purchasing. Now, once we assign these variables, it makes it very easy to actually put these variables into equation form. So we're going to write the equation now. So in order to find the total cost, we're going to say C is equal to, the cost is equal to $1.19 times B. Okay, we're looking at the total number of bottles B. So depending on how many bottles you buy, that's going to influence your price. So $1.19 per the number of bottles you buy. All right. Now we're going to evaluate the function for 15 bottles. So if we're trying to find the total cost for 15 bottles, we simply have to type in 15, B equals 15. We're going to plug that in to that function. So I'm going to say C is equal to $1.19 times 15 bottles. And so if I do that in my calculator, I'm going to say $1.19 times 15. That is going to be a total of $17.85. Nice and easy. So I know that sometimes taking a situation from a word problem and putting it into an equation is somewhat difficult, but again, just think about what you're doing, think about what the situation is. Always determine kind of what your operation is going to be first. So if you're looking at this example, for example, we're looking at each bottle costing a certain number, and we want to figure out, well, how much am I going to pay if I have 15 bottles? That tells you that you're going to have to use multiplication because you're multiplying the price by the number of bottles. In the example when we were talking about lunch and splitting up the bill, obviously if you're trying to split something up, that key word right there tells you that you're going to have to divide. You're going to have to make that number smaller, okay? So just kind of think intuitively about what's happening, what operation you're going to be using, and then always assign your variables first, and then try to put that in equation form once you've assigned your variables and figured out your operation. Moving on to your last example, example number 9 today, renting a car. If you rent a car for 1 day and drive it 100 miles, the cost is $45. If you drive it 150 miles, the cost is $57.50. So obviously different costs depending on how many miles you drive. So first, this says we want to fit a linear function to the data points. And then for part B, we want to use the function to determine how much it will cost to rent the car for 1 day if you drive it 200 miles. Okay, so we're given 2 different coordinate points essentially from the intro to this problem. So this says if you rent a car for 1 day and drive it 100 miles, then the cost is $45. So I have an ordered pair right here. If I drive 100 miles, that's my input, my output is going to be $45. Okay, so that's going to be my first ordered pair. Now, I also have another ordered pair. If I drive 150 miles, the cost is going to be $57.50. So then I have an ordered pair, 150 as my input, 5750 is my output. So I have two different coordinate points here that I'm looking at. I'm looking at 100 miles and $45, and I'm looking at 150 miles and $57.50. Now I can use these two ordered pairs to find the slope of what this graph is going to represent. So the slope of this graph, and then I can put that in slope-intercept form or in point-slope form, okay? So if you think back to Algebra 1, you might remember that we did point-slope form and slope-intercept form. And if we plug in that slope in a couple of points, we can actually find what the equation of this situation is going to be. So let me go ahead and use the slope formula. So the slope formula, if you remember, is m equals y2 minus y1 over x2 minus x1, thinking back to Algebra 1. So if I plug in these values, I'm going to say this is x1, this is y1, this is x2, this is y2. If I plug those in, I'm going to have x2 is 5750 minus, or sorry, y2 is 5750, y1 is 45, so 5750 minus 45. x2 is 150 minus x1 is 100. Now, if I go ahead and do the math there, I have 5750 minus 45. That is going to give me 1250 or 12.5 here. Over 150 minus 100 is obviously just 50. And if I calculate that, 12.5 divided by 50 is just going to give me 0.25. So my slope here is going to be 0.25. Now I'm going to put this in point slope form so I can go ahead and find an equation that represents this situation. So if you remember back to Algebra 1, point slope form says y minus y1 is equal to m times x minus x1, okay? These y1 and x1s are just going to be points on the graph, so you can plug in either of these two ordered pairs. I would probably plug in this one because it has cleaner numbers. Don't mess with decimals, seriously. I will hunt you down if you mess with decimals. You're going to make your life much harder than it needs to be. Always just go for the clean one. 100 comma 45 is going to work perfectly fine. So what we're going to do here, we know what our m is, right? Our slope is 0.25. We already figured that out. So I can plug in this slope right here to where I see m. Then I can plug in these 2 points, x1 and y1. So I can plug x1 in for x1 right here. And then I can plug y1 in for y1 here. So let me go ahead and plug in everything. So I'm going to say y minus my y1, which is 45, is equal to my slope, which is 0.25 times x minus x1, which is 100. Okay? Now, I can go ahead and convert this into slope-intercept form. All I have to do is I have to take care of this parentheses, and I have to combine like terms, get y by itself. So what I'm going to do first, I'm going to multiply this 0.25 to both terms inside the parentheses. So I have y minus 45 is equal to 0.25x. And then 0.25 times negative 100, that is going to be negative 25. Now I'm going to get all of my terms on the same side. So if I add 45 to both sides, whatever I do to one side and must do to the other, I'm going to have y equals 0.25x. And then 45 minus 25 is just going to be plus 20. Okay, so this is going to be my equation that is represented by this situation. Now for part B, this says use the function to find how much it will cost to rent the car for 1 day if you drive it 200 miles. So essentially what I'm going to do is I'm going to plug in 200 for x because I'm trying to see how much it's going to cost if I drive 200 miles. So all I'm going to do is I'm going to say y is equal to 0.25, and for x I'm going to plug in 200 plus 20. Then 0.25 times 200, that's going to be 1/4 of 200, which is 50, plus 20. And then 50 plus 20 is equal to 70. Now, always remember, since we're talking about a numerical value, a dollar value, right? I always want to include the dollar sign. This is going to be $70. Okay? So that is how we are introducing you to relations in 2.1. If you have any questions, go ahead and hop on to office hours or let one of us know. Thank you guys. We will see you next time.